So yeah, I'm a local here in New York City, and for those of you who don't know me, you'll get a chance to know me a little bit better next year if you're here at the Flatiron, because I will be actually doing sort of a half-time sabbatical next year here at the CCA, which I'm very excited about. Usually, my sort of day job is looking for exoplanets and studying exoplanets. I have a group at Columbia called the Cool Worlds Lab. You'll hear about some of my students and the research they've been doing today. The theme of my talk, I mean, I'm mostly well known for my research looking for exomoons, which of course is sort of somewhat of a new frontier to try and detect these objects. But this has sort of led me down this path of just more generally, how do you detect weird signals? Because exomoons are kind of strange. So I'm going to be sort of describing some more generalized approaches towards the end of my talk of just finding weird stuff in your data, whatever form it may be. So why is the weird interesting? We have many examples of this, of course, in astronomy. I think when you detect something truly serendipitous like this, like the first detection of pulsars or fast radio bursts, similar to what we kind of heard about earlier. Another example closer to my field was the detection of Boyagin's star, the WTF star, these very strange flux dimmings. Of course, in every single case, people first say it's aliens, and then they work their way down the list of other more reasonable hypotheses. But it is true that all of these examples do kind of, as an astronomer, make the heart beat a little bit faster. This is kind of, I think, where some of the most interesting discoveries often happen, and often revolutions happen in our understanding from discovering the one-off, extremely strange objects. So that kind of motivates why I'd be interested in these things. It's kind of, we don't think of exoplanets as weird, but actually they were weird. Certainly when I was an undergraduate and we were first starting to hear about exoplanets being discovered, with this, for example, the very famous discovery of 51 Pegasi b, which was the first hot Jupiter and the first planet discovered around a normal star, a main sequence star. And it was hardly anticipated. I mean, people really didn't expect there to be Jupiter-sized planets parked so close to the star, and it kind of caused theorists, of course, theorists had ways of explaining it in a post-hoc way, but it really wasn't predicted. And indeed, actually, it is true that the origin of hot Jupiters is still an issue of debate. And I would say that back then exoplanets were kind of weird, but they've changed over time. In 2 decades, we now have, as probably you all know, many thousands of discoveries of exoplanets, so things really have changed. There's this kind of nice plot that Eric Mamajak has been popularizing at conferences and on Twitter and things. Here's a screenshot of it. And it's the rate of discovery of exoplanets over time. And he argues that there's essentially a Moore's law happening here for planet discovery. So maybe it's a self-fulfilling prophecy, much like Moore's law. And the actual rate of discovery is increasing, so they're doubling times every 27 months. And what that means is that you'd hit 1 million exoplanets by 2034 and 1 billion planets by 2057. And when I saw that, and you hear about, okay, well, Tesla's coming online now, it's starting to find planets. WFIRST will probably find many more planets, and we have Plato. Many planet hunting missions are still being planned right now. So this looks, set to continue. It's not unreasonable that this might continue for many more years. But what's the point of it? I mean, I do think it's important that we ask ourselves that question, honestly. What is actually the value of having a catalogue of 1 million exoplanets? Do we actually learn anything significant from that compared to just having a few thousand? Now, I know I probably shouldn't say that as someone in the field of exoplanets. I should be telling, let's just keep building more and more exoplanet missions, that's all that matters. But I do like to pause and think about this. So I sort of have 3 answers to this as to why you might want such a large catalogue. One might be maybe unfairly calling it the 1%ers philosophy. Certainly a lot of people studying atmospheres, I think, adopt this philosophy, especially people looking for like Earth-like planets, that there are a few, and only a few objects which are really interesting. And the vast majority of planets, just throw those in the garbage. Only the closest, brightest stars, the ones suitable for atmospheric characterization matter. Everything else, it doesn't really matter. So you might just look at the local stellar neighborhood, for instance, as the relevant population. The other philosophy you might have is more of a big data philosophy. That's probably a philosophy I guess folks at the CCA would actually probably more be in line with. This is that the value of these data is that we are performing a census. We're collecting demographics and thus understanding a population as a whole. That will lead ultimately to the greatest insights. It's not those 1%ers that will help us have the greatest insights. It's the whole population that will really do this for us. And then finally, to come back to the idea of the weird, it would be an even more extreme case than the 1%ers. It's really those one-off, those extremely strange events, the needles in the haystack philosophy. Here's Oumuamua. It's not an exoplanet, but You get the idea that these kind of one-off weird events, those are the ones that people tend to gravitate towards and really will advance our understanding the most. So 3 approaches. I'm not going to say any one of these approaches is better than any of the other approaches. They're all reasonable things to do. I think it might be worthwhile, if you're early on in your career, sort of pausing and thinking about which of these philosophies are you putting your energy into, because they do require quite different skill sets, I think, to sort of master each one of these. So I'm mostly going to ignore the 1%er philosophy. If you've had people come here and talk about atmospheres, I'm sure you have, that's pretty much what they're talking about. I'm going to mostly talk about, and I really mean observational atmospheres, I should say, to be fair, when I say that. I'm mostly going to be talking about the sort of, the kind of special events, the needles in the haystack philosophy. But before I do want to advertise that in my group we certainly do spend a lot of effort also on this more big data approach. So let me just say something about that first and advertise a particular project we've been doing in my group about this. So big data, again, I'm going to sort of, we have this subset of 3 different approaches. I'm going to further split it into 3 different ways of doing this big data. This is not necessarily exhaustive, but 3 popular approaches you find in the literature. One is to kind of take the frequentist approach. Maybe you might look at a population of objects and apply some kind of KS test, things like this, to try to distinguish if you have significantly different populations. Here's an example where they actually have a sliding KS test to try and make subdivisions of exoplanets. A lot of people have concerns about frequentist statistics, though. I mean, it's not necessarily faithfully capturing the information or representing the information that's embedded within these data sets. So you might think, okay, well, a better approach is to go full Bayesian. Let's build a giant hierarchical Bayesian model. That's certainly something, if David Hogg was here, I'm sure he would be largely in favor of. If you can't afford to do a full HBM, you might approximate it. So an approach called approximate Bayesian computation, ABC, which can sort of help you get around that a little bit. And then you can design a population model. So these parameters are parameters describing your entire population. What is the mean radius of exoplanets, say? What is the power law distribution of the mass distribution? So these are ensemble properties you're trying to learn, and you infer them from the population. And finally, again, this is not exhaustive, but a final approach I might advertise is to think about information theory. Information theory has certainly been sort of developed with looking at large data sets in mind, in particular language. When Claude Shannon was developing information theory, that was really what he was thinking about. That is a very large data set, a corpus of text from which you're trying to decipher meaning. And we can make the same analogy when we look at exoplanets and think about information theory to do this. So let's give an example of this. Here's 2 planetary systems, 2 real planetary systems discovered by Kepler. Kepler 80 and Kepler 20, so this is the size ordering of the planets. This is not necessarily to scale, but you get the idea. We have the smallest planet on the inside, the largest planet on the outside. This is, intuitive. This makes sense when we look at this picture. This is kind of what you might naively expect exoplanetary systems to look like. And then you have Kepler 20. And Kepler 20 made a lot of news. It was announced from, I think, David Charbonneau's group at Harvard a few years ago. I remember being sat in the room when they made this press briefing that really kind of surprised us, that you had this Jupiter-like planet and then a much smaller planet and then another Jupiter-sized planet. It seemed really weird, like nature shouldn't be building this. And yet, there's a lot of these objects out there. There's plenty of these things being found. So we have this intuition that this should be somehow an ordered system. And this is a disordered system when you look at this. And so you might say, well, this is low entropy, this is high entropy. That's really what we mean here by ordered and disordered. But that's just intuition. Can I actually quantify those statements? So that's what we spend a bit of time thinking about. Probably the simplest thing you could do, just purely based off the ordering of these planets and their sizes, is just to tally up whether the planets are getting bigger or smaller. So if the next planet along is bigger, I'm going to increase my score by +1. If it's smaller, -1. And I do this, I get a score of +4. If I do this here, I get a score of 0. It all kind of cancels out. And there's actually lots of ways of getting 0. I could swap those 2 over. I could swap all these guys over. And I could do that, and I still end up with 0. In fact, there's 66 ways I could rearrange this and end up with 0. There's only one way you can rearrange this and get a score of +4. So by sort of the Boltzmann definition of entropy, we can say that this is therefore the log of the number of ways of achieving this corresponds to a high entropy system, and this is a low entropy system. So could we now, with this metric, go around and start defining how ordered planetary systems are? This gets a little bit complicated. That was a 5-planet system I showed you. One state is that it has essentially 66 ways of being configured and giving you a tally score of 0. And the other extreme is that it had a tally score of a tally score of +4, and there was only one way of achieving that, and there's an intermediate state here and negative sides here. Repeat for all multiplicities, and you get this. You get this giant triangle, so you can actually have, like a 10-planet system. You could get a tally score of +1, and there's a ridiculous number of ways of rearranging things to get that. And it actually turns out, and I don't really have a derivation to prove this, but it actually turns out that it follows this sequence known as the Eulerian number sequence. The way I found that was actually literally, it's embarrassing, but I just literally typed in this number sequence in Google and just kept going through and finding the Eulerian number sequence worked. And then I tried like a few ones, like 11 and 15 or whatever, to see if it was still working, and it works beautifully. So I can't actually QED prove this works to infinity, but I'm pretty sure this is the right description for this. It seems to work really elegantly. So that's useful, so now I can apply this. So if we apply it to the solar system, unfortunately, things don't seem to work because the solar system has a tally score of -1. And you can see why. It kind of goes up into the size of Jupiter and then more or less down the actual solar system. That's kind of unfortunate because we look at the solar system, we don't think it's disordered. What if I idealize the solar system? What I mean by that is I'm going to replace Mars here with a super-Earth. Why would I do that? If you're familiar with the Graham-Tack scenario, it's kind of thought that Jupiter came in quite deep into the solar system, actually truncated the growth of Mars. So if it was not for that situation, Mars would have grown larger and potentially grown into a super-Earth. And even in this perfect kind of staircase situation, I still end up with a very high entropy score. So this seems like it's not working for the solar system. And thus I modify this system now to account for the integral under the tally. So this is the sort of the tally history as we go across from the innermost planet up to Jupiter, and then all the way out to the outermost planet. And now I'm going to take the integral under that curve, which is the area, and use that in addition to the tally. So I now have a vector, which is the tally and the integral score, to define each microstate. When I do this, this really does help. It brings the entropy of the solar system way down to just 35 ways of achieving this now. So we apply this to a sort of a fake system here. What I'm doing is I'm starting a system off that's completely ordered system, and I'm allowing at each iteration there to be a 10% probability of a swap between two systems, some kind of dynamical exchange. And as you can see, overall entropy increases. This is over many, many trials of doing this. The colored regions are sort of the credible intervals after doing this. And you can see that, as you would expect, entropy increases with time. Certainly the ensemble entropy increases with time. That's sort of an important definition check that you want to make sure if you're coming up with a proxy for entropy. So what that means is if I look at this most extreme system here, this is the entropy of 0. Even if I do 10 to the 6, a million experiments, and I evolve this system for a while, it never goes back to 0 entropy. It's extremely unlikely, if you allow a system to have random exchanges, it would ever just randomly go back to a completely ordered system, which kind of intuitively makes sense. And what that means is that when you look at a system like this, it's completely ordered. It's highly improbable that it is the product of random exchanges. It was most likely born in this situation. So we could have that it was born and there was no exchanges in positions, or we could have that it was born disordered and there were multiple exchanges in positions and it somehow led to this. But from this experiment, it shows this is extremely unlikely to happen. It's really difficult to imagine how you could get this ordering just by random chance. This has to be a product of some memory of its history. There is a caveat, and that's often with entropy calculations, Maxwell's demon can get in the way. You could have a demon which sort of stops the chain once you reach a 0 entropy state. Assuming that does not exist, there's no Maxwellian demon playing God on these systems, then this is highly unlikely to happen by chance. So I guess the point here is that if you observe a system like this, you can claim it's a non-random architecture, and thus it has some memory, some information content within it about its original formation pathway. Now that might sound like an obvious statement, because when we look at exoplanet populations, we basically assume that it's teaching us something about how they formed. But it's not necessarily true, and that's kind of what the point of this exercise was, to demonstrate that. let's look at the Kepler systems.
So let me ask you one.
Sure.
So if you have a lot of exchanges, right? Then it's likely that you throw out basically all the planets, or a large fraction of the planets. Right?
Oh, you mean through like scattering or something?
Yeah, scattering, right? So I mean, like, is there any understanding of planetary formation which assumes that there's a huge amount of scattering of large bodies? I'm not aware of it, but it could be wrong.
There's a huge amount of scattering of large bodies.
Large amounts of rearrangements of them.
I don't know about a huge amount. Depends what you mean by a huge amount.
Well, I mean like basically your argument from the viewpoint of Boltzmann theory, right? In order to get this defined entropy, you have to have a lot of exchanges. Right?
Yeah,
so,
yeah.
I mean, like, is there any scattering theories in planetary formation where there are lots and lots of exchanges?
Well, I guess in the Nice model, you certainly do have exchanges.
Yeah,
I'm not sure
not
if
a lot, right?
I'm not sure exactly how we define a lot. There's certainly not an order of a million exchanges. That's certainly true. But that's not really the important point. The really important, I would say, the important point is that you cannot obtain this configuration through a product of random exchanges. It's not possible that this is some that a system that was born in a wholly disordered state, such as Kepler 20. Where is that? Kepler 20. This kind of system here. That cannot be expected to reasonably evolve, at least by random chance, into a configuration like this through random exchanges. However many exchanges, whether it's a few exchanges, 1 or 2 exchanges, or a million, it doesn't really matter how many. It's not going to end up in that final configuration by random coincidence.
Right. So let me give you another example. So for instance, let's say you have a goblet cluster, right? So in goblet cluster, the phenomenon known as core collapse, right? Where basically everything sinks to the bottom, lightning rises up, right? So that arguably is a low entropy state, okay? Right? But the system will gravitate toward that just because of the physics of that exchange, right? So not clear to me that that this thing has that much meaning yet, right? Until you account for some of the physics.
Okay. Well, I mean, we can. The other thing we can do with this that we sort of link more to the physics side. I wasn't really going to go into this too much today, but one thing we can link to the physics side is to actually apply this to Nice model products, which is something we actually kind of touch on in the paper as a way of quantifying what is the expected size ordering. This is really a metric for quantifying size ordering that you see in systems. And when we apply it to the simulations that we see from the Nice model, you tend to find that the systems are born in rather ordered states. So the question is, if you see an ordered state now, after 4 or 5 billion years of evolution, presumably, what we're trying to test here with some kind of quantifiable metric is whether that is a product of simple random exchanges, however simplified that cartoon picture may be. It's kind of a catch-all statement to say something happened that we don't understand that could have moved it from a disordered state into this present ordered state, or is it most likely that it resided in that system in the first place? This is kind of what the tool's trying to capture. I'm going to move on just so I don't get too... We can talk about this maybe afterwards later on, but I want to sort of get into the weird stuff a little bit as well. So I just want to finally advertise, but if you run this on the Kepler systems, there's kind of a lot going on in this plot. Let me just break it down. This red histogram is the fraction of random systems. This is Kepler 3-planet systems. This is the fraction of randomly generated systems which have this entropy score, which is 0, log 1. This is the fraction of randomly generated, just let them swap for many, many times systems that would have this particular entropy score, log 4. And what I'm looking at here is the actual Kepler multis with these circles and the dynamically packed subset of those Kepler multis, which we know we have essentially a complete sample. And you can see that the Kepler multis are indeed more ordered than one would expect as a product of random exchanges. And you can actually quantify this in a variety of ways. You can take the mean entropy, you can use an Anderson-Darling test, or you could do like a likelihood test. When you do this on all the systems, you get a consistent picture. The takeaway is that the Kepler systems are significantly lower entropy than just random exchanges. That there is definitely some memory of their formation pathway embedded within the architectures that we're looking at from Kepler. If you want to learn more about this, I'm going to direct you to this paper, or happy to talk to you afterwards about this a bit more. But to come back to the main thesis of the talk, which is to look for the weird, the needles in the haystack, I'm not going to talk about Oumuamua, but a similar type of very unusual event, because we have no examples of it to date, would be an exomoon. This is obviously something which sort of inspired this line of thinking. So over the last few years, I have been looking for this. We have a program called the Hunt for Exomoons with Kepler. I guess maybe now it's Hunt for Exomoons with TESS or something, I don't know. That we've been looking for exomoons. This is an example of what an exomoon detection might look like. It's not a real detection, it's a simulation. It's really pumped up on steroids, if you like, and really exaggerating how to make things as feasible as possible. I have 6 transits of an exoplanet. This is a Neptune-sized exoplanet orbiting an M-dwarf, and I have an Earth-like moon. And you can see there's big moon dips, and there's also wobbles of the planet. That's the transit timing variation effect as a result of the gravitational influence of the moon. So we can simulate all of this stuff with a code called Luna. When you run this and you actually try to apply it to real data, you have to be really careful. And that's because this is a nested model. So I don't know how many are familiar with what I mean by that term, but a nested model really means that I could always set the moon radius and mass to be equal to 0, and I would recover the original, more simple model, just a planet by itself. That's a nested model. Whenever you have a nested model, it's really easy to overfit, because you're guaranteed by adding in the extra degree of freedom to get a better fit. You can't get a worse fit if you have a nested model. It's like fitting data with a second-order polynomial and then going to a third-order polynomial and saying, oh, I get a better chi-squared, yet you have to. You can't not get a better chi-squared if you do that. So that's sort of an important caveat. We're in the same situation here. So you need to penalize the degrees of freedom in some way. The most rigorous way of doing this is to use a marginal likelihood calculation. I won't explain this too much, but you can use a code called multiness to do this, that essentially converts this very horrible integral into sort of a trapezoidal rule integration, which is nice and easy to do. Another approach is to cross-validate. You can only do that if you have lots of data, but here essentially you do a fit on, say, 4 transits. This is a KY1876b, and you can see that the moon fit is trying to pick up on something here. It thinks, oh, maybe this is the moon. This is what I mean. Whenever you do a moon fit, you'll always find moons. It's like it's guaranteed to always find something. So it starts to pick out these dips. They're not very convincing. You forward propagate the model, or you interpolate it on missing data, and you see how well its predictions are doing. And you can see the predictions are terrible. It's not explaining the data any better than the simple planet model is. What you shouldn't do, I really strongly urge you not to do, is to use reduced chi-squared. It's very popular, I know this. It's completely the wrong tool for this. There's a paper that goes really nicely into detail about why this is wrong. This is not a linear model. You can't use reduced chi-squared on non-linear models such as this. It's kind of like doing like Newtonian physics in the vicinity of a black hole. Like it's a special case scenario that works under certain conditions, but it's not the general case, and it's certainly not going to work when you're dealing with complicated non-linear multimodal models such as an exomoon. So I really strongly urge you not to use reduced chi-squared if you can avoid it. You will end up with erroneous model selection. You have to pick some planets. There's 4,000 planets to look at, potentially from Kepler. This is their period and their sizes. These are the planets we have tended to focus on out here on the right-hand side. The reason why is because we do a calculation to make sure a moon would be tidally stable for 5 gigayears. That depends on the Hill sphere. The Hill sphere is obviously bigger out here. And also, you want a bright star. So some of these grey dots are just too faint. It's not really plotted on this axis. You can't see magnitude here, but some of these stars are just too faint. So you want a bright star, plenty of signal to noise to work with. And we did that for years. I mean, this is like, it was 2015. We surveyed, over 2 million CPU hours, a lot of time using Pleiades and stuff. We surveyed 16 planets, and we hadn't found anything. But we had these sensitivity curves, I guess, which was something. This is the fraction of cases which were achieving the mass ratio plotted on the y-axis here. So you can see that if I want to say, well, how often are you sensitive to sort of 10% mass ratio? That's the same as Pluto-Charon. I can do that in about 40% of the cases that we looked at. Earth-Moon, that's a 1%. We can do that about 1 of 8. But the Galilean moons, anybody know where the Galilean moons lie in this plot? What's the mass ratio of the Galilean moons to Jupiter?
Way down.
Way down, yeah, it's up here. It's 10 to the minus 4. So we have no ability to detect Galilean moons through their dynamical effects. This is the mass ratio. So I'm talking about gravitational influences here. And the Kepler data just is not precise enough to pull that out, I'm afraid to say. So this was kind of disappointing. You can turn this into upper limits, I suppose, but it's unclear how necessarily useful these are at this point.
So why
Yeah.
does it require 2 million CPU hours?
Oh, good question. That's because, for one thing, when you calculate the Bayesian evidence, you're doing a n-dimensional integral. So this integral here is marginalized over all of your free parameters. In our case, we have 14 free parameters. This is a 14-dimensional integral. You also have to do what's called a photodynamic simulation of the system. It's a 3-body problem. So that also eats up a bit more CPU time than a vanilla fit. So it ends up being expensive. Yeah.
Does it help to try to use more sophisticated integration algorithms?
I mean, we already use a very simplified restricted 3-body problem solution for the actual n-body dynamics. People are always iterating on different approaches versus multi-nest. We can talk about that afterwards. There's other codes since multi-nest that have been released that claim better scaling with dimensionality. We haven't experimented with those too much, to be honest, because as I'll hopefully convince you, there's sort of maybe a different approach of doing this. So a different approach is to think about the population. There's this great paper by Simon and Gula-Zeitman in 2011, and later René Heller built upon this idea that if you have a bunch of transits with a moon and you stack them, then you might get this kind of winged structure on the end, and that's because the moon's sort of bouncing back and forth, and you get this ensemble average signal. Okay, so we could look for that, but the problem is, by definition here, you can see I'm stacking n greater than 1 transits, and typically the planet I'm looking at tends to be pretty long, like a few hundred days. I mean, that's where we think moons should be. And Kepler only looked at one patch of the sky for 4 years, so there's actually very few cases where you have this statement be true, that you have n greater than 1 transits. So what do? You do the last trick of all astronomers, you start to stack different data sets together, which is pretty much what we do here. So we stack 284 different planets together to see if there's an ensemble population of moons around this ensemble population of planets. So it's sort of asking more of a statistical question when you do this. So you'd rather not do this, but it's sort of a last resort that we all use in astronomy when there's no other technique left. So when you do that, this is what you get. This is the outer transit flux. I've sort of mirrored it on itself. Outer transit flux, so this is right on the edge of the transit sort of contact points. This is going out. I've rescaled it into planetary radii, its sort of distance, if you like. And this black line is the signal we would expect if 100% of these Kepler planets hosted an exact Galilean clone moon system. Okay, 100% have exactly the moons around Jupiter. Put them around these planets, what would you see?
So that's a 10 to the minus 4 mass ratio, is that what you mean by?
Yeah, I mean, this isn't really an issue of mass ratio though here, because this is the shadow of the moons.
Okay. Yeah.
So this is more an issue of what is the radius of these moons in front of the star.
Okay.
That's actually the most important factor here. This is, you know, a 10 ppm effect, like it's very, very small.
But
But
what if the star fluxes change? Like, does it affect what you predict?
yeah, so you have to be very careful with that. I'm sort of skimming over that giant detail that if I only talk about Exomoons, I spend a lot of time talking about. You have to be very careful how you detrain the data. We actually started out with like 1,000 planets. We ended up with 284 because the 284 are the ones we believe we can do a good job on the detrending. That is a big, careful thing you have to be looking at when you're dealing with this. But we think we did a good job because when we bin the data, the noise is like really beautifully behaved. So we actually do think we've done a good job with the way we've stacked this data. And as you can see, it's flat, so we don't have any moons, but we can turn it into an occurrence rate, and it turns out that the upper limit to 95% confidence is about 2 out of 5. Less than 2 out of 5 Kepler planets have Galilean moon systems around them. And that's an empirical result. So that's, I think, probably the most constraining actual measurement we have of exomoons to date from the population that Kepler has given us. So no signal, that's kind of disappointing. And I think that leaves us with this situation that if we look around a star and we look at these 3 different regions, hot Jupiter kind of planets, we basically have ignored those, as I've sort of highlighted earlier. I have not surveyed those planets for exomoons. If someone wants to do that, knock yourself out. I'm just not going to do it. The intermediate periods, we've looked really hard and we don't see anything. We've really pushed data as hard as we can, we think. We think moons are not necessarily extremely rare, but somewhat uncommon. I think that's probably a fair statement. So that either means that, you know, planets form here and they rarely form moons around them for whatever reason, or I think more likely they're probably, especially the gas giants, they're forming beyond an AU, beyond the snow line, migrating in, and something is causing it to lose their moons in the process as they migrate inwards. And what that means as a conclusion, I would say, is that it's pretty much crucial to survey this region in the future. So I think this is the future of exomoon hunting, is going to be those cold planets, those planets that live beyond the snow line. That's unfortunate because they're intrinsically rare. Because of the geometric probability of getting a long period planet transit at the start, very unlikely. We have like half a dozen of those things. But they're so special, especially the Jupiter ones, that I really think they deserve a lot of attention with missions such as Hubble and James Webb. We could really, these things transit once every 3 or 4 years. We could just look at it for 20 hours and really complete a whole survey of those things. Now, you're probably thinking, maybe you saw this if you're following the field. Okay, you said there's no exomoons, but I thought there was something about an exomoon. So we had this paper out in Science in the fall last year. So let's just talk about that. There was one object out of those 284 that was interesting. It was this guy. A priori, it was already interesting. You might not know this, but Jupiter-like planets are rare. Only 7% of Sun-like stars have them. So this already was an unusual object. It's a Jupiter-sized planet in our sample. Not only that, but it's long period. That's also very rare. Only about 14% of Kepler planets live beyond 0.1 AU, just to show how strong the detection bias is. And not only that, but we could tell it was close to circular. So a priori, it was kind of everything we would want for a moon-hosting object. There's very few objects like this. Not only that, when a posteriori, it was interesting as well, because when we look at the individual sort of flux decrease around each transit, we notice that this guy really stands out. It's like a 4 sigma outlier. Seems like there's some kind of carving in flux going on around the edges. But the problem is it implied a very strange moon. The moon was weird. It was 4 Earth radii, size of Neptune, a moon. And it was, we actually measured the mass with some photodynamics, about 30 Earth masses. My student nicknamed this Neptune for fun. And it was pretty interesting, but obviously we didn't feel convinced by this because it was just so bizarre. So we actually asked for some Hubble time to sort of go after this object. And Alex Tichy, my student, really led that observation. So we used the wide field camera 3 to do that. There's some systematics which really get in the way of doing a clean job of this, but let's go through it. There's 3 important systematics. There's breathing effect, which is essentially like thermal variations as it goes around its orbit. There's some kind of visit long slope, which nobody knows what's causing that really. It's basically it's uncorrelated with any onboard measurement on board the spacecraft, so we don't really know what's causing that. It could just be intrinsic stellar activity. And then there's a hook effect, which is to do with charge trapping happening inside the CCD. Or really the detector, it's not really a CCD because it's infrared. So this is the breathing. It's very obvious in your images. Here's our target. The light's been spread out through a grism. So we can do atmospheric characterization potentially on this. And you can see this huge breathing effect, which is actually fairly straightforward to remove. You just take the median flux because it affects the entire plane sort of homogeneously. We take that off. Then you have hooks to deal with. You can see this. This is the photometry you get after removing that uncorrected. This is of another nearby star. You can see the transit, right? Even without doing any correction, transit of the planet, very, 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 very clear and obvious. But you can see this like kind of color-coded here, this kind of exponential hooking effect. We can remove that. It's typically done with an exponential hook, literally an exponential model. It does a pretty good job. That's pretty much what everyone in the literature does. Gets you down to 440 ppm. We come up with a new approach, kind of a non-parametric approach. I'm happy to chat to you afterwards about that. I don't want to get into too much detail about it, but it does do significantly better. It gets us down from 440 to 375. So we're actually quite excited to start applying this to some archival data as well. As you can see, the comparison star also does pretty good using this. This is almost 4 times better than Kepler, the precision you get out of Hubble. Not surprising. It's 2.4 meter aperture, right, versus 0.95, so it's not surprisingly it's significantly better. Something weird is going on here. This kind of immediately stuck out to us, and there's nothing here. So that was kind of odd, but that's just a visual glance. There is some kind of sloping here, but that's most likely the visit long train, and this seems to be like reversing the gradient. There seems to be something going the other way at this point. It's kind of odd. So the next thing we have to deal with is this overall trend in the data. Typically, people do this, linear, or this, and almost that's the entire literature, is to do one of those 2 approaches. Neither of them are obviously physically motivated. They're just sort of heuristic models to sort of deal with it. If you do either of these, you get a big dip on the back end of the transit. We also tried a third model, an exponential, and we see the same thing. So there's apparently some kind of flux decrease compared to the overall trend that you might model. So that's kind of interesting. I was just going to put the evidences on here. Yeah, here's the evidences. The evidences is essentially the odds ratio of this being an exomoon. So imagine doing e to the power of that number, whatever that is. That's the odds ratio that the moon model is favored over a planet model. So it's actually very significant there's a dip here, according to this. The actual significance of the dip is about 5 sigma on this side. Also, the transit comes in 76 minutes too early, which is kind of odd. This is the Kepler timings. Following a straight line, we'd expect it to be on this point. This is the epoch we measured. It comes in way too early compared to this straight. It's 76 minutes off that straight line, if you extrapolate it up. So it's quite a significant TTV. It's about 4 sigma. It's still difficult to measure this, though, so it's a 25-minute error. So there's apparently a TTV and a moon-like dip. I'd also highlight that this dashed line is where we would expect the planet to transit if it was on a linear ephemeris. This solid line is where it did. That's the midpoint of the actual observations. Now, notice that it essentially comes in early, and the moon comes in late. That's exactly what we would expect. They're orbiting a common barycenter. The barycenter sits between them, so that they're kind of saddling either side of that barycenter as they go across. So the phase of the moon dip, the moon-like dip, appears consistent with the TTV observation at this point. So this started to look kind of interesting at this moment. Of course, the obvious thing was like, this could be an instrumental, right? Maybe it's just the spacecraft just did something funky and it's tricking us. What I can say is that it does not appear to be instrumental, although, caveat, we cannot prove. How can you prove, really, absolutely, that it is definitely not an instrumental effect? It's almost impossible to do so. The things we looked into, though, is seeing if the centroid positions did anything funky. This is actually the instant in time where the moon-like dip occurs, and the centroids are very stable here in both X and Y. Nothing strange going on. We also checked if the dip was achromatic, if it appeared in the red end of the data versus the blue end. It does. We see it on both channels, no matter how you detrend it, doing all 3 detrendings. We looked at our residuals very carefully to see if they were Gaussian. As far as we can tell, the noise behaves very Gaussian when you include the moon, and very non-Gaussian when you don't include it. And why is that? It's basically because there's a dip here. You can see it. This is the residuals without a moon. And it's basically there's this huge feature here which is not modeled by the data, and thus it makes your residuals look terrible if you don't include that feature. And then the solution appears physically self-consistent. We get a radius for the moon, a mass of the moon, a radius for the planet, a mass of the planet from the photodynamics. All of those line up with a physically self-consistent solution. And finally, as I did highlight earlier, the comparison star is completely stable at this moment in time. So there's a lot of checks we tried. We have like a 90-page supplementary materials go through all of this. You can trawl through it if you're interested. We've done some new checks which are not in the paper, I'll just highlight. We checked if you do a detrending in XY pixel position rather than time, what happens. And again, the moon signal persists when you do that. We also tried checking if this could be an additional transiting planet that Kepler missed. What's the chance that there was a Neptune-sized planet that is just on an orbit around the star? It just came in at that moment in time and tricked us. That's less than 0.75% probability. We did some Kepler injection recovery simulations recently to test that. Stellar activity, this is a very quiet star. It's less than 200 ppm photometric variability per quarter. It's a very quiet star, so I don't think that's likely. And finally, it was actually independently recovered in a new paper by Rennie Heller and his collaborators. They see the same dip. They just went right back to the raw FITS files and did their own reduction. There's a very slightly different shapes here, but it's essentially there is some kind of dip happening after the main transit. So this still isn't convincing, I think. I think we want to still see it happen again to believe it's real. This is the observation we took, taking out posteriors. This is the dip we saw. This is sort of where it's located in time. This was the next event. Now you can see our next event, we actually don't predict it would transit. There's only a 25% chance it would transit the following event. So we did not ask for Hubble time for that event because we thought it was a waste of time. The one after, though, was pretty interesting. That was actually the one, it's actually happening next month in May, is transiting. We asked for Hubble time because we have a very clear prediction that it should come in pre-transit based on our models. And if we saw it come in pre-transit, and that was the prediction of our model, I think we'd have a real slam dunk case that this was the right model. Unfortunately, we were not granted the telescope time, so we can't do that. And pretty much only Hubble is the only game in town for this, I'm afraid. As we go forward in time, you can see things get bad because we can't now tell the difference where it's going to be. As you propagate the model forward in time, the uncertainty grows. I don't think we'd ever be able to confirm this now without, unfortunately, basically going back to scratch and recovering the original moon data set. So, bad decision by the TAC. But unfortunately, it's going to be very difficult to confirm this. So just in summary, the cons of this is that because the...
You might mention, is it TTT variation consistent with the Neptune-sized exomoon?
Yes.
Ratio?
Yeah, we measure the mass ratio between the planet and the moon that way. It's 1%, and it's consistent with Neptune's, and it's about 20 or 30 Earth masses. So there's pros and cons to this case. I'm not sold this is a real exomoon yet, but I think it's pretty interesting. I'd say the cons is that because the HST data is so great, that's actually a pain in the ass because it dominates your regression. When you have one data set that's way better than all the others, that actually kind of screws you over because that one data set completely drives the inference. So what if that one data set was funky somehow? Also, the observations we took were frankly unprecedented in terms of duration. Nobody has stared at a transiting planet for 40 hours with Y4 camera 3 before. So it may just be that the telescope did something it's never done before because it's a fairly unseen, a new type of observation. We don't see the moon come back up again. I'd love to see the moon transit and then a nice flat line afterwards. Of course, our scheduling cut us off, so we don't see that. That would be far more convincing. And finally, this is still a Neptune-sized moon, and nobody anticipated that from theory, so this bothers me a lot. It's kind of weird. On the plus side, we have a TTV anomaly. It's 4 sigma, a dip, 5 sigma. The moon hypothesis explains both self-consistently, so you have one theory that can explain 2 observations. The dip does not appear to be instrumental as far as we can tell, independent recovery from other teams, comparison star checks, a lot of other stuff. And as far as we can tell, the solution is self-consistent. But even so, we did not call it a detection. This is evidence for at this point. And it's tentative, but I would really like to see someone try and get more observations of this to confirm it before I believe it. And I guess, as is often the case in astronomy, more data is needed before we could actually claim this is legit. But it is exciting that Hubble certainly has the capability of doing this. And this may as far as we can tell, this really doesn't have any issues with potentially being the first discovery. So, exomoons are neat. How am I doing on time? I have like 10 minutes to speed through into the other weird stuff now. So exomoons are great, but what about other weird? I promise you some other weird stuff. So, Tabby star. Tabby star is an example of a very weird object. Has this bizarre dip. How was it found? How do people detect that? In the case of this system, actually we use planet hunters for exomoon searches to a certain degree as well. It was spotted by this group, the planet hunters, which just look online at a website like this and see if they can see anything like this, like a big dip, and then they click yes, no, do I see anything odd, and make comments about it. And this was an object that was detected that way by the power of citizen science. That's fantastic, but it's not really scalable. Like there was 200,000 Kepler stars. That already was a challenge for the public to deal with. What do you do when you have 20 million, which is Tesla's going to deliver, or hundreds of million in the future as LST starts to get going? So it's going to be very challenging to scale this approach. So you might want an algorithm to do this rather than people, and you have to ask the question: well, what's the merit function? What's the cost function? What am I minimizing when I do this minimization? How can we classify a star as strange? Conventionally, you'd write down a likelihood function, and then you'd try to regress some model to the data. So what's the probability, essentially, of getting my data given some model and some choice of parameters, theta? And in a simple case, like a chi-squared, it'd just be weighted least squares or something to do that. Now, that's great, but what if you don't have a model? I mean, what is the model for this? What are you fitting to it? This isn't a transit. That's not going to work too well. So ideally, you want a model which is somehow agnostic, and it can find any type of signal, which is just distinct from a flat line. That's your ideal capability here. So we have an approach, we think, that can somewhat do this. It's called the weird detector. We weren't very imaginative with the name. And the idea is to sort of build upon the principle of coherence. So if I had a signal, let's say this is my signal, and it's sort of almost like a lensing event, like a peak up here, and I'm going to assume this is strictly periodic. That's a really important assumption in everything I'm about to say. This algorithm will only work for strictly periodic things. That's pretty much the only assumption we have in this piece of work here. I have many, many events, and I'm going to stack them on the correct period. And if I take a running average, once stacked on the correct period, you can see that the data is essentially less scattered about that line than it would be for some other random choice. So the data is more coherent about this correct period than some arbitrary, erroneously picked period. So what that means is you can use an approach been sort of used in other fields as well called phase dispersion minimization, which really quantifies this. When you directly measure what is the chi-squared of these data points about this f' model, which is essentially a candidate signal, as we call it in the paper. So it's basically like a running average or a running median that you run through the data. That has issues because you have to think about the bandpass and the kernel size you use, of course, when you do this, but it's a fairly robust approach. Okay, the problem with just doing this alone, why isn't this the end of the story, is that this detects a crap load of rotating stars if you do this, because they're also pretty coherent. I mean, if you phase fold stars, they tend to look like that anyway. So this isn't really a weird detector, this is just a star detector at this point. That's not really what we want. So we somehow need to make this preferentially find short duty cycle events, which is really what we wanted in this paper. So to do that, we think about the distribution of the data. So at the correct period, if I bin the data up on the correct period, or phase bin it, and I take a flux distribution, because it sort of dipped down or dipped up, and I take the histogram of those binned points, they'll be very highly tailed. There'll be a high tailedness to the distribution. Versus if I chose a randomly picked period, and then I binned on that wrong period, the data would basically appear completely symmetric in a histogram of those data points. And you can actually quantify how tailedness a distribution is with something called kurtosis, which is the fourth moment basically of a distribution. And we can actually build this in then into our PDM as an extra term to look for, which is going to preferentially find short duty cycle events, essentially. You can see it kind of scales it. D is the duty cycle, scales very strongly with d to the minus third, d to the minus 3. So it's going to really like a short duty cycle event. So that's basically what weird detector is in a nutshell. It's PDM, the PDM cost function multiplied by the kurtosis, plus a bit of bootstrapping to get the significances when we actually go through some periods. What do we find? So we've actually ran this on 200,000 Kepler stars as an example. This was not periodic, but we detected it anyway because of that kurtosis trick. And you can see this is actually 3 different stars that apparently have exactly the same event at almost the same time. It's just very slightly different in time. What's going on? We plotted where these stars are, and it actually turns out to be a comet that almost overlaps this. So this is almost certainly a brightening event caused by a comet passing through the field. We, of course, not only detected that comet, which has already been known, but we run it on the Kepler stars, remove all the known signals, see what we get left over, and we get some weird stuff. This is actually the 18 new signals we found in the paper. You can see this is sort of one orbital period of whatever this thing is. It's a 36-day period object in this case. It's pretty much flat apart from a pulse, which happens, but a fairly long duration pulse. We don't really know exactly what this is. Our best bet, although we haven't done detailed modeling, is this some kind of heartbeat binary situation going on. There's some kind of either a high mass planet or a low mass star is swinging in on an eccentric orbit, and as it swings in, it tidally pulses the host star, and that makes it more luminous for a short interval of time. And that's maybe what we're seeing. We've seen certainly plenty of heartbeat stars before. This is sort of a more extreme case because the amplitudes are so low here. They're typically like 100 parts per million, whereas most heartbeat stars kept reported are order of several percent variations. This is somehow a very low amplitude version of those, but we're not really sure that this is necessarily the only example. One thing that slightly bothers me about it is that the morphologies are so similar to each other. If it really was a heartbeat binary, you'd kind of expect more of a distribution of shapes. These tend to be suspiciously self-similar. So if you have any other ideas about what this could be, that'd be a great thing to, I'd love to hear about that over wine or something, or in the questions. So we did not detect any analogy of Tabby star. We do recover Tabby star, but we don't find any other Tabby stars, unfortunately. Would have been great, that's what I was hoping for. We didn't find those. But we've got 20 million test stars that we're running on right now, so we'll see if we can find more examples from them. When you see something like this, let's say you detected it, the next thing you might ask with a weird signal is how do you interpret it? So Tabby star, well, theorists like to have fun with these things, and they can fit it. I mean, the original paper just did like 50 or 60 comets or something, and I mean, you get a good fit. If you have 50 comets, there's a lot of free parameters. Yeah, you get a really nice fit. Or you could do like asteroids, or some kind of disk, some belts, or even a Dyson shell or sphere or something. And yeah, you can get a really good fit with a Dyson sphere, but it's kind of an infinitely tunable model, right? Isn't it? Of course you can get a good fit. So again, we wanted to approach this from a new angle and say, is there more of a data-driven way of interpreting these signals rather than imposing some assumed model beforehand? And my student Emily Sanford's been thinking about that a lot. I think the dream would be to take a photo of it. If you had an actual image of whatever it was that was causing those transits, you'd be done. And there really wouldn't be any issue about model comparison. You just have an image of the damn thing. So that's what we wanted to do. One way you could potentially do that is to imagine a pixel grid like this. Each square here is either empty, which means there's no material there, or it's full. So there's something opaque here. I'm going to transit that entire grid across this star and see what the light curve looks like. This is an example of doing that. So that's fairly straightforward. That's the forward model. Forward model is straightforward. What about the inverse model? That's of course going to be more challenging. Now this gets really hard because, as you can probably imagine, there's lots of degeneracies in this problem. Emily actually came across some interesting new ones that haven't been discussed too much. This I think is fairly well known. There's a flip degeneracy. I could move this triangle upside down. I could flip it upside down. I'd get exactly the same signal as long as I flip it about that axis. But I can also flip columns of it and do the same thing, or just individual pixels and do the same thing, or even, this is almost like a quantum superposition, if you like, of all of these states where each pixel is now half opaque. So this is a half opaque pixel down here, half opaque pixel here. That also is exactly the same as this. So that's like an intrinsic degeneracy in the problem. There's no way of getting really around that. So if you see this, what you would expect to recover is this for a perfect reconstruction. So that's just unavoidable. There's also this issue of an arc degeneracy. So this is a planet transiting a star, gets this familiar light curve shape. Now let me show you another shape which will create exactly the same light curve. It's going to be this. If it will play, here we go. That mathematically is exactly the same as a box-like transit. There's no difference whatsoever. The opacity is distributed as a sine function along here. So it's basically opacity 1 here, and then it goes off as like sine of the latitude as you go down. And that Emily discovered that actually perfectly reproduces. There's a perfect arc degeneracy that exists in this problem as well. That's a pain in the ass, but whatever. So we try and deal with it. So we try injecting some true signals, simulating what their light curve look like, and we tried so many different algorithms. This is actually just a subset of everything we tried. We probably tried like 20 algorithms in trying to find a way of recovering these things. I'm just going to highlight this one particular one, SART. This is what we do in tomography, computer tomography in the hospital. You have a CT scan. That's the algorithm they use to take the 2D slices that they do, the X-ray slices, into a 3D reconstruction. This is the algorithm they use. It's essentially a linear algebra type algorithm. But Emily came up with a few others, this kind of arc averaging approach, trying to exploit these arc degeneracies more cleverly, and even like a pure brute force combinatorics approach, where you just sort of try every possibility you can and see in a brute force way what comes out. You can't explore every permutation, but you can kind of explore some subset which you think is reasonable. So what we find is that the SART algorithm does really well if it's dusty. I guess there isn't really an example of that here. If you have something that's kind of semi-opaque, this tends to do best. If you have something that's like solid like this, you can see that this algorithm tends to do the closest reconstruction to these things. So I mean, that ring is fairly well reconstructed with this algorithm. So let's apply it to Tabby star. What does Tabby star look like? That was kind of the question that really drove us here. This is the Tabby star data. We tried our different algorithms. You have to fit for this velocity term. That's kind of a difficult one to deal with, but there's some certain speed at which this pixel grid goes across the star. You have to sort of learn that as you go. But this is our image. So this is the SART algorithm run. You cannot really get a good fit to the data using these more discrete algorithms. We find that you really need a dusty algorithm to make this work. And it's kind of interesting. It has structure. Now, when you look at this, you might think this is an arc degeneracy, but it is not, because the arc degeneracy should be double over like this. So this is most likely real. This is not the product of the arc degeneracy. It shouldn't really do that. When we apply it to another event, we get a very similar star thing. I should have also included, we did this on TRAPPIST-1, where there's actually 3 planets transiting across the star at the same time. And you actually really beautifully see all 3 planets individually resolved using this. You do not get these shapes when you apply this to other data sets. So we really think this is kind of interesting and potentially a real reconstruction of what's going on. But then that's as far as we went, and we sort of left it to the theorists to sort of say, hey, what the hell is this now that we've given you this? So happy to talk to you about that afterwards as well. So I want to stop there, because you've been very patient with me going through all that. This was the comic book which I gave to Adam Wheeler. He's at Columbia. You should invite him to tell you more about this code, the work he's been doing with Melissa Ness here as well. This was a comic book which I found, The Weird Detector, not quite The Weird Detective, and has the subtitle, The Stars Are Wrong, so it seemed very appropriate. I'd like to give a present to my students when they finish. Alex over at Columbia has been working on this Exomoon problem, and Emily is thinking both about this shadow imaging approach and also something else, I have to chat with you, called planetary linguistics, applying natural language processing to the architectures of planetary systems. So with that, hopefully leave you a few threads that you can talk to me about afterwards. Thank you very much.